This is problem 11-30M. It's on page 633. It is planned to use an aluminum channel, given there, it's a C section, as a column having a length of 4.24 meters. The ends can be considered to be pinned. The aluminum is alloy 6061T4. Compute the allowable load on the column for a design factor of 4. All right, let's see. It's a C102 by 2.586. It's 6061 T4. And let's see, what else? Length, 4.25 meters, and it's pinned. Let's see, design factor N is 4. Okay. Now, a big hint is that this is an aluminum channel. So what failure theory do you think we should use?
The aluminum association.
Aluminum Association's recommendations. There we go. So let's go do it. Page 623. Now I may be a little slower at this one because I've not used these before. Let's see what we can do. Notice they recommend a factor of safety, but we've got a factor of safety here of 4 that's imposed upon us. So that will change FS a little bit. But the equation that we use is dependent upon the slenderness ratio, so we should go ahead and calculate it. The slenderness ratio is still the same thing. It's the effective length divided by the radius of gyration. Now we will, again, want the minimum radius of gyration. If the ends are pinned to pin, then what is the effective length? Well, not 1, it's 1 times the actual length.
Yeah.
Okay, it's just the actual length. So this would be 4.25 meters for the effective length. And then we need the radius of gyration, which we'll have to go back to the cross-section properties to find. So let's look for an aluminum C channel that matches what we're given. We are in metric units, so page 707 looks appropriate to me. 102 by 2.586 is line E. Everybody reference row E? Okay. Now they give us something kind of nice here. Do you notice what they've given us? They've given us Rx and Ry. Okay, so we don't have to calculate the radius of gyration R. Which one should we select, Rx or Ry?
The minimum.
Whichever one's smaller, that's right. So 16.26 millimeters. And let's see, there's 1,000 millimeters per 1 meter. So that'll get rid of all the millimeters and meters. And now we can calculate the slenderness ratio. So please put that in your calculator, see what you get. Should be about 250 or so.
261.4.
Okay. 261.4, and that is non-dimensional. So there's our slenderness ratio. Now if we go back into the text, oh, by the way, while we're here, let's grab the cross-sectional area. If they've got it, yeah, they've got it. We may need that, I'm not sure. 954 millimeters squared. Hopefully that'll save us some time later. I'm not sure if it will or not. Yeah, it looks like it will. All right, short and intermediate columns, well, that's a slenderness ratio between 0 and 66. Long columns greater than 66, that's what we've got. We're supposed to use allowable load over area equal 352,000 over this. Now I'm a little bit confused because they've got a number in them, or in the equations. I see. What they've done is they've used equation 1116, it looks like, with a factor of safety of 1.95 to generate equation 1118b. Since we're not allowed to do that we won't be able to use this equation. We'll have to go back and use 1116 itself. Pi squared E divided by the factor of safety, LE over R squared. So I think basically what we want to do is rearrange and solve for the safety factor. No, wait a second.
We have our safety.
Yeah, we have it. We were given it. It's 4. I'm thinking of the last problem. So I'll have to plug 4 in there. And the question is how much load will it take? So all we'll do is we'll move A to the other side. Okay? So now we need the elastic modulus. And I'm a little confused because I'm thinking that the yield strength should come into play somewhere. No, just the stiffness because it's a long column. Never mind. All right. So notice that the effective length over the radius of gyration is just our slenderness ratio. And so we should be able to do this pretty easily. We just need the elastic modulus for aluminum. And again, since it's metric, I don't have that memorized. Elastic modulus for most aluminum alloys, including 6061, is 69 gigapascals. So pi squared 69 gigapascals multiplied by A, 954 millimeters squared, divided by the factor of safety of 4, and then divided by the slenderness ratio squared, 261.4 squared. We should end up with a load in what units? Gigapascals times millimeters squared. So what units? Kilonewtons. That's right. So plug it into your calculator, please. See what we get. Pi squared times 69 times 954 divided by 4 divided by 261.4 squared.
I got 2.38 kilonewtons.
Anyone second that? 2.38 kilo? Okay. All right. So there's the load that channel could take. Questions, comments? Does it seem like a low load? Does it seem small? I know you don't really have a feel for kilonewtons, but in the last problem we had, what, 31 kilonewtons or something? Remember, there's two differences. Here we're talking about aluminum. The size of this is not terribly large.
134.9 kilonewtons an hour.
Yeah, that it could actually take.
Yeah.
Right. Actually, wasn't that the critical load? I don't remember. Anyway, it's a big difference in the number, right? What's the difference? Well, this is a very different cross-section. Right? It's not necessarily as efficient a cross-section as the last one. Plus, of course, the last one is steel at 2-inch by 3-inch rectangular area. Now, I think this channel is actually a little bit taller, but it just doesn't have as much material as aluminum. So it's not as stiff.